Hello guys, welcome to our today's discussion. Today we are going to look at linear transformation and we are going to continue with our previous topic, integral calculus. The objective of today's lesson are, by the end, you as a learner should be able to define linear transformation, then identify various vector spaces in various vectors in vector spaces, and prove if a given transformation exists or not. So without taking much time, I'm going to the definition of linear information, which is basically an operation that changes a vector space to another. It can also be thought of as a function that converts a given vector or a matrix to completely a different vector, provided that the rule of that space are maintained. So basically, this definition means, in a mathematical point of view, that if T is a linear transformation such that T transform a vector in Rm to Rn vector space, then we need to prove the following two rules. One, if we take two vectors, u and v, such that u and v are in Rm space, and we give them transformation T, should give us the same way if we take an individual vector u, we transform it under T, then we take the sum of it plus the vector u, v, transform under T. The second rule that we need to prove in order to say that a given transformation exists is, if we take a scalar, let's say beta, and we multiply by transformation of one vector, let's say u, then this one should be equal to beta multiplied by that vector, then you give it transformation T, provided that vector is in R space. R here means real number. So let us get the concept of vector spaces. And as I said earlier, R stands for real number, and therefore any vector chosen from here must have elements found in a set of real numbers. So n to power r to power n, the superscript n here is an integer, and it can be from 2 to 3 up to n. For instance, you can take an example of R space, R2 vector space. That means if you take a vector v, it must have two elements. For example, v is equals to 2, 3. So you can see here we have two elements. You can also take maybe p vector is equals to a, b. So that means it has, vector p has two elements. If you take vector in R3, you can also make sure that you have three elements, 2, 3, 5. So let us take this example and you see how to prove whether vector space exists or not. So show that vector T transform a vector space in R2 to R3, and that one is defined by, you give it a vector with the R2 xy, it will transform it by taking the value of x, you minus the value of y, then you get the value of, this one will stand for x value, and the value of x you take and you add it to value of y to stand for y, then you take the value of x, you multiply by 2 to stand for z. So at the end of the day, you'll be having two vector space, 3 R3 vector with 3 element x, y, and z after transformation. So solution, here we only need to prove the two rules, rule 1 and this rule. Then if the two rules exist, or if they're true, then we can conclude that the given vector T is a linear transformation. So let us look at the calculation part of it in order to prove. So the first one, we need to prove rule 1. This rule here, if I may go back, this one here. Let us prove it. So suppose I have two vectors, u and v. So let's v be 4 and 4, 2, and v be 6, 3. So I want to prove that if I add the two vectors and I give them transformation t, so you take the two vectors, you give them transformation, the summation of two vectors, you give them transformation t. Therefore, you'll get the same equation if you transform each vector and you give them transformation individually. So this t plus v plus u is 4, 2, 3, 6 will give us 10, 5. So when I give them transformation t, by taking the value of x, I subtract the value of y, which is 5, take the value of x plus the value of y, which is 10 plus 5, and I multiply the value of x by 2, I will get this vector. So that is 5, 15 to in R space R3. So that we can call it equation 1 here. Then we need to prove that if we take these individual vectors and we give them transformation separately, then we find the sum, we'll get the same answer. So u transformed will give us 2, 6, and 8. This is u transformation. V transformed will give us 3, 9, and 12. If we add, we get the summation of the two vectors, we'll get 5, 15, and 20, which is the same as the answer that we got here. So from there, we can say equation 1, this is equation 2. We can say equation 1 is the same as equation 2. So rule 1 is proven. So we go to rule 2. Rule 2 says if we take a beta is a scalar in a real number such that we multiply vector times the beta, then we give it transformation t is the same as we multiply beta. If we take beta and multiply by the vector u, then we transform. So let us take an example. We want to take vector u, which is 4, 2. Then we give it transformation first. And when you give it transformation, 4 minus 2, 4 plus 2, and 4 times 2, we'll get 2, 6, 8. Then we multiply by the scalar 2 here, and we are going to get 4, 12, and 8. We call it equation 3. So let us take the beta, we multiply by vector itself, then we apply transformation t. So if you take the vector u is 4, 2, we multiply by 2, which is the scalar, we get 8, 4. If we give it transformation t here, we are going to get 8 minus 4, 8 plus 4, and 2 times 8, which the result turns out to be 4, 12, and 16, which is the same as the one that we got here. So you can see equation 3 and equation 4 are also equal. So by that, we can say that equation 3 and equation 4 are equal, and therefore the second rule is also satisfied. Hence, we can conclude that T is a linear transformation on R2, taking R2 to R3. So from there, I think that is how we can prove that a given vector space is a linear transformation. And maybe to sum up, from the above example, it should be noted that transformation changes vector from one space to another. Then another thing that you need to note is that a vector space of Rn means the vector of that space has n elements. Then to prove that a vector, a transformation T is a linear transformation on a vector space V, we need to prove these two rules. So when these two rules turns out to be true, then you can say that vector space exists. If one of the rule does not meet or turns to be false, then it does not exist. So you take note on this. Down there is assignment for you guys, will be collected next week. That is the end of our discussion today. Thank you.
Thank you.
Any question?
No question.
Thank you, sir.
Thank you.
Thank you.